Am I audible properly, guys? Audio and video both are clear. So good evening to each and every student. First of all, tell me, am I audible properly? Audio and video both are clear to you people. So in this series, we are studying signals and system in very much comprehensive manner. Okay? And from today, we are going to discuss Continuous Time Fourier Series. Already we completed 2 chapters, chapter number 1, chapter number 2. And from today, we are going to start our 3rd chapter, that is Continuous Time Fourier Series, and which is very much important. So first of all, tell me in the comment box, am I audible properly? Audio and video both are clear? Okay. So before starting the chapter Fourier series, first of all, we'll understand the basic thing. Why we have to study the Fourier series and what is the benefits of studying the Fourier series. What are the different reasons behind the studying the Fourier series, and why we have to study the Fourier series? What is the advantage of Fourier series? Okay, so this thing first of all we need to understand. So first of all we will see one video, okay, and from that video we will understand, or directly you can watch on YouTube also. Later on you can watch on the YouTube, okay, just to search Fourier series animation, okay, and the screenshot of that video I will explain in this class why we have to study the Fourier series. So Fourier series first was introduced by Joseph Fourier, the great mathematician Joseph Fourier. Okay, so what is the basic circular convolution we will cover in DFT. Don't worry, once we study DFT, then circular convolution we will cover, so don't bother about it. Okay, so first of all, what is a Fourier series? Just wait for a minute. Am I audible properly, guys? अभी आवाज आ रही है? आवाज आ रही है, guys? Tell me now, audible properly? सही से आवाज आ रही है अभी? बताइए तो. Tell me now. Audible? Please confirm in the comment box. Now audible properly? Now clear? Fine? Okay, very good. Okay, now audible. Okay, very good. So let us continue further, guys. So first of all we will study what is the reason, or what are the different reasons behind the studying Fourier series. So I am recommending one video, guys, that video you can see on the YouTube channel. simply search Fourier series animation, guys. Fourier series animation 3D. This video you can watch, guys. Later you can watch. Later you can watch this video. Fourier series animation. Okay, it will help you to understand Fourier series better way and whatever content available in this. Okay, whatever content in this that I will explain in this class, guys. Okay, don't worry. So just search Fourier series animation and then you will find this video. Okay. This video you can watch, guys. This is very interesting video. Okay, it will be very much beneficial for you. Okay, now let us start, guys. Later you can watch this video. Okay, now let us come back to our topic, Fourier series. Okay, now Fourier series. So what is the Fourier series, guys, and why we have to start studying the Fourier series? So basically concept is what? There are two types of signal. One is periodic, another one is aperiodic. In periodic also, again there are two types of signal. Sinusoidal periodic signal and non-sinusoidal periodic signal. Sinusoidal periodic signal means sine and cos. It is known as sinusoidal periodic signal. And non-sinusoidal periodic signal means rectangular function, triangular function, sawtooth waveform. These all are the non-sinusoidal periodic signal. Now each and every non-sinusoidal periodic signal, can be converted into harmonically related sinusoids. Again I am telling, each and every non-sinusoidal periodic signal like rectangle, triangular waveform or rectangular waveform or sawtooth waveform, each and every non-sinusoidal periodic signal can be converted into the harmonically related sinusoids. Harmonically related sinusoid means what? Sine omega 0, then sine 2 omega 0, sine 3 omega 0, sine 4 omega 0, sine 5 omega 0. These are known as what? Harmonics. Okay, infinite number of sine and cos both, guys. Okay, so this concept was first introduced by the Joseph Fourier. Even any aperiodic signal also, guys. Any aperiodic signal like u of t, signum function or exponential increasing decreasing function, each and every continuous time as well as both discrete time, aperiodic signal also can be converted into the harmonically related sinusoids, but there is a different concept. Okay, so first we will see how we can convert non-sinusoidal periodic signal into the harmonically related sinusoids. Correct? So see, first thing, this thing available in video also, guys. This is simple sinusoidal function sin theta, and each and every sinusoidal signal has some certain frequency, certain phase difference as well as amplitude. So if this is the sinusoidal function, already I told you, guys, already I explained you, this is what peak amplitude. Correct? This is like Vm. Okay, this is Vm, peak amplitude, positive peak amplitude. This is like minus Vm negative peak amplitude. Correct? And here, this is from here to here, this is what your fundamental time period, capital T. This is the fundamental time period, capital T, and inverse of fundamental time period is nothing but your frequency, fundamental frequency omega 0. This omega 0 is nothing but 2 pi by f, and 2 pi by f is nothing but 2 pi by capital T, guys. Correct? Like this. Okay, so these are the parameters of this sinusoidal function, like frequency in hertz, frequency in radian per second, suppose additional phase angle, and angle theta. Theta is nothing but omega 0 t. Here we can say this theta is nothing but what? Here on x-axis is theta, so this theta is nothing but this omega t, guys. So theta is nothing but omega into t. Correct? Okay, so this is the fundamental time period. Inverse of the fundamental time period is fundamental frequency f0 and omega 0 also, guys. So this is simple sinusoidal signal. Correct? On x-axis you can write t also, guys. Function of theta, instead of function of theta you can write it is a function of t, guys. Okay, this is very much important concept. So this is simple sine theta. Okay, now here I am changing the amplitude, guys. 1 by 2 sine theta. Previous signal was a simple sine theta having amplitude Vm. Vm is equal to suppose 1 volt, and here this is minus 1 volt. Clear? And let us consider now changing the amplitude. Again, it is also sinusoidal signal, same with the same frequency. There is no change in frequency, only change in amplitude. Now this peak amplitude is 1 by 2, and negative side it's minus 1 by 2, guys. Nothing there. Okay, again it is a sinusoidal signal with the same frequency, but thus just a change in the amplitude. Fine. Now next signal. Now here I am adding the additional phase angle pi. Additional phase angle. So additional phase angle pi already we have seen in the first chapter, guys. Just shifting by this sinusoidal sine theta, right side by pi or left side by pi. Here this is theta plus pi, so shifting sine theta left side by pi amount. Correct? Shifting this sinusoidal function left side by pi amount. This is 0, this is angle pi, okay, and this is 2 pi, guys. Angle theta equal to 2 pi. Okay, so just shifting this sinusoidal signal left side by pi, then it become sine theta plus pi, guys. Correct? Shift by left side by pi unit, then it will be theta by sine theta plus pi. So simply this is what additional phase angle. Again here also there is no change in frequency, guys. Frequency again omega 0. Correct? Fundamental frequency omega 0, just additional phase angle. So first sine theta, then we change amplitude from 1 to 1 by 2. Now we are changing the phase from 0, additional phase angle from 0 to pi. In all three cases frequencies remain same, omega 0, which is very much important, guys. Correct? This is also sinusoidal function but different additional phase angle. Now here I am changing the frequency, guys. Now it is sine theta by 2, guys. Sine theta by 2. Now theta by 2 means what? It is nothing but omega t by 2. So now your fundamental frequency is, we can say, omega 0 divided by 2. If the fundamental frequency is half, then the fundamental time period is double, because frequency and the fundamental time period are inverse of each other. So here half frequency, and we are increasing the fundamental time period. Now see here, fundamental time period as compared to sine theta, it is 2 t, guys. The fundamental time period of sine theta is t, then here it is 2t0. Now we are changing the frequency, it is sine theta by 2, guys. Okay, similarly you can write sine theta by 3 also, or sine theta by 4 also, or sine 2 theta also, guys. Simply here the fundamental time period with compared to sine theta, it is now 2 times t0. Again amplitude 1 volt, and here minus 1 volt, suppose. Clear? Now this is the interesting part. This is very much interesting part, guys. Now what we are going to do here, we are adding two sinusoidal signals with different amplitude but same frequency. One sinusoidal function is 3 by 4 sine theta, and here frequency of this signal is omega 0, and here one more sinusoidal function 1 by 4 sine theta, and this signal also have the same frequency omega 0 but different amplitude. We are adding, this is the first point, we are adding two sinusoidal signal having the same frequency but different amplitude. Then the resultant signal also will be the same sinusoidal function, or sinusoidal function with the same frequency. The resultant signal will be sine theta only with the same frequency. The resultant signal, see this is 3 by 4 sine theta, and here 1 by 4 sine theta, both the signal have the same frequency. Here omega 0, here also frequency omega 0. The resultant signal will also be another sinusoidal function with the same frequency omega 0. Of course there is a change in amplitude. Now it will be what? 3 by 4 plus 1 by 4 sine theta, you can take common, so it will be sine theta. The resultant signal is simple sine theta, guys. Correct? The main point is we are adding two sinusoidal signals having same frequency but different amplitude. Correct? This is the first point. Fine? This is the first point. Now next, so here you can see, now if we add two sinusoidal signal with same frequency but different amplitude and different phase angle. Different amplitude, different phase angle, but the same frequency. In this case also, we will get the sinusoidal signal with the same frequency. Correct? Okay. Even phase angle also different. You can see here, this is sin theta plus 1 by 4 sin theta minus pi by 3. Then also the resultant signal will be sinusoidal, another sinusoidal signal with the same frequency. Okay, this is omega 0, here also omega 0. The resultant signal will also have the frequency omega 0. Of course, there is a change in phase and amplitude. Okay, but the important point is what? Same frequency. We are adding two signals having the same frequency. So this is the conclusion. So long as two sine waves have the same frequency, two sine waves have the same frequency, important point, same frequency, their sum will always be another sine wave. There sum will always be another sine wave of the exact same frequency. Exact same frequency means what? Here omega 0, here omega 0, and the resultant signal will also have the same frequency omega 0. But of course, but with different amplitude and phase. Of course, different amplitude and phase, guys. Amplitude can be different, phase can be different, but the important point is frequency remains same. Correct? So this is the first point. Is this clear? All of you tell me in the comment box. Is this clear? This is very much important, guys. Fine. Now next point. This is very much important. Now if we add two sinusoidal function having a different frequency, then the resultant signal will be no more another sinusoidal function. This is very much important. Suppose one function is sin theta, another function is sin theta by 2, then the resultant signal will no more the sinusoidal function, it will be the another function. This is very much important. So here it is written, if we add together sine waves of different frequency, this is very much important, different frequency, then the resultant waveform is no longer a sine wave. Like this, you can see here the resultant signal is no longer a sinusoidal function if we add to different frequency sinusoids. Correct? Different frequency sinusoids. Say for example this one, here first signal has the frequency omega 0 and the another signal has the frequency 3 omega 0. You can see here, this is sin theta means omega 0, and here sin 3 theta, that means 3 omega 0. Now we are adding two sinusoids but different frequency, then the resultant signal is no more or no longer another sine wave. It is a different waveform. Okay, it is a different waveform. Fine. Now next, guys, in the similar way, if we add multiple sinusoids with the different frequency, like this is omega 0, this is 2 omega 0, this is 3 omega 0, this is 4 omega 0, and so on, guys, and so on, like this. 4 by pi sin theta, so here omega 0 frequency. 4 by 3 pi sin 3 theta, so 3 omega 0. Sin 5 theta, so 5 omega 0, and sin 7 theta, 7 omega 0, and sin 9 theta, so 9 omega 0, and so on, guys. These are called harmonics, guys. Omega 0, 3 omega 0, 5 omega 0, harmonics, guys. Okay, harmonics. This is the third harmonic, we can say. This is the fifth harmonic. 7 omega 0 means seventh harmonic. Intentionally, we took here only odd harmonics intentionally, guys, so that we can get the particular non-sinusoidal periodic signal. We are considering only here, important conclusion is what? First conclusion is we are considering only discrete frequencies. We are not considering all the possible frequencies. See, first we are taking omega 0, then directly 3 omega 0, only discrete frequency, or we are taking 2 omega 0 suppose. We are not considering 1.5 omega 0, 1.65 omega 0, the frequency present between omega 0 and 2 omega 0. So here between omega 0 and 2 omega 0, infinite number of frequencies are present, like 1.1 omega 0, 1.11 omega 0, 1.2 omega 0, 1.31 omega 0. So we are not considering all the possible frequencies due to certain reason. We are considering only discrete frequencies. Discrete frequencies means first omega 0, then directly to omega 0, then directly 3 omega 0. Here intentionally I took only odd harmonics. I am not considering even harmonics. Intentionally I am not considering. We are not considering 2 omega 0, 4 omega 0, 6 omega 0. We are considering discrete frequency. In that also we are considering only odd harmonics intentionally. Later we will, in the another example, we will consider all the harmonics, but important point is only discrete frequencies. Here all the possible frequencies are not needed. Okay, this is important point. So here we are adding, so you are getting here, you can see here this, the resultant signal is no longer a sinusoidal, it is a different waveform, and you can get the prediction from this. It is nothing but it will later on it will be converted into the square waveform, square wave. So again here it is 9 omega 0, 11 omega 0, then again you can see it is 13 omega 0, 15 omega 0, sin theta, sin 3 theta, sin 5 theta, sin 7 theta, okay, and so on. The resultant signal is no longer sine wave, it is somewhat a square wave. You can see here square wave. In the similar way we are adding again 15 omega 0, 17 omega 0, 19 omega 0, 21 omega 0, 23 omega 0. So you can see here the resultant signal is now it is closest to the square wave. And if you add infinite number, similar way, if you are infinite number of sinusoids, infinite number, series means what? Infinite number of sinusoidals, sin 3 theta, sin theta, sin 3 theta, sin 5 theta, 7 theta, 9 theta, 11 theta, 13, 15, 17, 19, infinite number of sinusoidals, then the resultant signal will be, it's a square wave. The resultant signal is square wave, correct? Square wave, it is periodic but non-sinusoidal. Periodic but non-sinusoidal. So conclusion is what? We can represent these non-sinusoidal periodic signals into harmonically related sinusoids. Harmonically related sinusoids, guys. You can see here. This is what? This is simple square wave. Square wave, guys. And this non-sinusoidal periodic signal is represented in the harmonically related sinusoids, sin 3 theta, sin 3 theta, sin 5 theta, sin 7 theta, and so on. But why we are representing this non-sinusoidal periodic signal into harmonically related sinusoids? Because in LTI system, later we will see sinusoidal steady state response, if your input to an LTI system is sinusoid, then output also sinusoid. So analysis of an LTI system will be very much easy if input is sinusoidal instead of square wave. If input is square wave, then it is very much difficult to analyze the LTI system. But if we convert non-sinusoidal periodic signal into the harmonically related sinusoids like this, then input is in the terms of sinusoid, and then analysis of an LTI system will be very much easy for us. So this is the first reason. Okay, two more reasons are there, later we will discuss. Okay, so conclusion is what? If we add infinite number of harmonically related sinusoids. Why it is harmonically related? Because here omega 0, then multiple integers of omega 0, like omega 0, 2 omega 0, 3 omega 0. So it is known as harmonics of sin theta, correct? And I told you guys intentionally we took here only odd harmonics, omega 0, 3 omega 0, 5 omega 0. In another example, and intentionally here it is only sine. It can be sine, cos also. It can be sine and cos both also, guys. Odd harmonics, even harmonics, both possible. In the subsequent module we will understand this concept. But here the important part is what? We can represent any non-sinusoidal periodic signal into the harmonically related sinusoids. And here conclusion is what? For this we required only discrete frequencies. Discrete frequency. We need not require all the possible frequencies, not require continuous frequency. All the possible frequencies means what? Continuous frequency. Only discrete frequencies are needed. Fine. Now let us take one more example. One more example I am taking. So now let's add together different set of sine waves. Now different sets of sine wave. One more example like sin theta, sin 2 theta. Here I am taking all the discrete frequencies, not only odd harmonics but odd and even both harmonics. 2 omega 0 it is even harmonic, 3 omega 0 it is odd harmonic. then this is even harmonic, 4 omega 0, 5 omega 0. Okay, now let us add different sinusoids, all the discrete frequencies, omega 0, 2 omega 0, 3 omega 0, 4 omega 0, and so on. So what will be the resultant signal? So the resultant signal will be like this, okay, omega 0, 2 omega 0, 3 omega 0, 4 omega 0, 5 omega 0. You can see here like this, omega 0 here, 2 omega 0, 3 omega 0, 4 omega 0. So the resultant signal is like sawtooth waveform, or we can say triangular waveform. Correct. Fine. So here you can see sin theta, sin 2 theta, sin 3 theta, and infinite number. If we add the infinite number of sinusoids, then the resultant signal you can see here, sawtooth waveform. In the first example, we saw that the resultant signal is square wave, but here it is the sawtooth waveform, or we can say triangular waveform. Correct. Now here the resultant signal is triangular waveform. Correct, one kind of triangular waveform. Fine, clear? Sin theta, sin 2 theta, sin 3 theta, 4 theta, 5. Again I am telling, only discrete frequencies are needed for this periodic signal. For periodic signal, only discrete frequencies. Correct? For periodic signal, this is periodic, previous example also was periodic. So for periodic signal, only discrete frequencies. Correct? Only discrete frequencies are required. And here only sine, because both are odd signal, that's why only sine. Later we will see. Correct? Cos also possible, sine and cos both also possible. Okay. So conclusion from these two example is what? We can represent any non-sinusoidal periodic signal into the harmonically related sinusoids, and for that we required only discrete frequencies, discrete harmonics, not all the possible harmonics, not all the frequencies, only discrete frequencies. If it is a periodic signal, then we required only discrete frequencies. And in the same way, if it is aperiodic signal, then aperiodic signal also we can represent into the different sinusoids. We can represent aperiodic signal also into different sinusoids, guys. But for that, for aperiodic signal like step function or exponential function, for that we require all the possible frequencies, discrete as well as integer, non-integer, both, omega 0, 1.2 omega 0, 3.2 omega 0, and so on. All the possible frequencies are required. So for periodic signal, only discrete frequency, and if it is aperiodic, then continuous frequency. This is very much important conclusion first. Okay, so here it is written in the two examples shown here, square wave and triangular wave. In the two example shown here, the sum of all sine waves happen to be repeating waveform. This is very much important. The sum of all the sine wave happen to be the repeating waveform, means periodic waveform, periodic signal. Sum of all the sine waves or sine functions happen to be repeating waveform, that means periodic signal. Okay, and for that we require only certain frequencies. In the two examples shown, square wave as well as rectangle wave, or again in this example also, the sum of all the sine waves happen to be repeating waveform. Here also, guys. Okay, here also. Fine. But in these cases, means for the periodic signal, in these cases means periodic signal. For the repeating waveform or periodic signal, in these cases only certain frequencies, I told you guys, only certain frequencies of sine waves were needed. Only certain frequencies means I told you guys, only discrete frequencies, omega 0, 3 omega 0, 5 omega 0, 7 omega 0, 2 omega 0, 4 omega 0. Only multiple integers of omega 0 were needed, not all the possible frequencies. Not required, because it is periodic signal. So for periodic signal, only discrete frequencies, and for aperiodic signal, all the possible frequencies are required. And each of sine waves had measurable amplitude also measurable. Correct? Finite amplitude. Now next, this is very much important, non-repeating waveform. See, this is a step function. Non-repeating waveforms can also be generated by adding sine waves together. As I told guys, as I told, non-repeating waveform also. Non-repeating waveform like step function and sinus, step function, exponential decreasing increasing function. Non-repeating waveform means what? Non-periodic signal. Aperiodic signal or non-periodic or non-repeating, all are same. So non-repeating waveforms can also be generated by adding sine waves together. But for this, all the possible frequencies are required. All the possible frequencies. That means continuous frequency. This is also non-repeating waveform, exponentially increasing. This is also non-repeating, means non-periodic, aperiodic signal by adding sine waves together. But in these cases, as I told, but in these cases, sine waves of every possible frequencies may be needed. Sine waves of all every possible frequencies, that means continuous frequencies may be needed. Okay, so here conversion of time domain to frequency domain, guys. Frequency domain means omega 0 to omega 0. Okay, so in this case every possible frequency is made needed. In this case means what? Which case? For aperiodic signal, non-repeating waveform. Okay, again I am saying, guys, in this case is sine waves of every possible frequency. See, every possible frequency, omega 0, 1 point omega 0, you can see here every possible frequencies, 1 point omega 0, 1.2, 1.3 and so on, guys. And each of these sine waves have an amplitude that is infinitely small, very very small amplitude. Okay, each case sine waves have that infinitely small amplitude. Fine, each and every possible infinitely small amplitude, guys. Fine. Okay, this is enough to understand. Is this clear? Okay, fine. Okay, so here now we can start the Fourier series concept here. Okay, so first important conclusion, guys. First important conclusion that you have to remember for all the remaining chapters. Conclusion from above explanation is what? Time domain, the signal representation in time domain, and we can convert the representation of the signal from time domain to frequency domain. Now we will understand the signal concept in frequency domain also, guys. Conversion of signal representation from time domain to frequency domain, guys. Time domain to frequency domain, conversion of signal. Okay, time domain T, guys. Frequency domain F or omega. On x-axis omega or F, and here on x-axis T. On y-axis in the both the case amplitude. In the frequency domain we will see the magnitude and phase. Magnitude versus frequency, phase versus frequency, and here it is amplitude versus frequency, guys. In time domain amplitude versus frequency. In frequency domain magnitude versus frequency or phase versus frequency or power versus frequency, guys. Okay, now the time domain representation of the signal is known as waveform. The time domain representation of the signal is known as the waveform. Correct? Is known as waveform, and the frequency domain representation of the signal is known as spectrum, like magnitude spectrum, phase spectrum, power spectrum. Okay, so here the signal representation is x of t. Suppose I am writing the Fourier transform. Suppose Fourier transform, say for example CTFT. I am writing for the continuous time, so that's why it is continuous time Fourier transform. If you are writing Fourier transform for the discrete time, then it is DTFT. Fourier transform x of f. On x-axis if you are taking f, then x of f. On x-axis if you are considering omega, then x of omega. So this is known as waveform, and this is known as spectrum, guys. Correct? See here on x-axis time, y-axis amplitude. Amplitude can be positive, negative, time can be positive, negative. Similarly, the frequency or magnitude versus frequency and phase versus frequency, guys. X of omega versus omega, or we can say here you are having x of f, then on x-axis it is f, guys. Correct? This is origin. Negative frequency, positive frequency, both possible. Okay, so here let us consider this is what n is the general signal. Okay, and here it is the Fourier transform. This is just example. Okay, this is just an example, guys. Okay, random example. This is what Fourier transform. Okay, Fourier transform. We are studying Fourier series, not Fourier transform. This is just an example. So this is what time domain representation of the signal. It is known as waveform. So here I am writing time domain representation of the signal, representation of signal is known as waveform. Waveform. And this is what frequency domain representation of the signal. Frequency domain representation of the signal, representation of the signal is known as spectrum. Correct? Is known as spectrum. So here there are two representation of the signal. In time domain it is known as waveform, and the frequency domain it is known as the spectrum. In the frequency domain it can be magnitude spectrum, phase spectrum, and power spectrum. Okay, so the conclusion is what is the important conclusion, guys? In time domain, and we can convert time domain signal into the frequency domain. Okay, transform. So I told you guys, if it is periodic, guys, just we have seen for periodic signal we required only certain frequencies, only discrete frequencies. Correct? For the periodic signal we required only discrete frequency, and vice versa also true, guys. Only discrete frequencies, discrete frequency. So in time domain if signal is periodic, then in the frequency domain it will be discrete in frequency. Correct? And vice versa also true. Vice versa means if it is discrete here, then it will be periodic here, guys. This is very much important. It is applicable for CTFT, CTFS, DTFT, DTFS, for all for all kind of transform. And similarly, just we have seen if it is aperiodic, guys, for aperiodic signal or non-repeating waveform, for aperiodic signal we require all the possible frequencies may be needed. Correct? All the possible frequency means continuous frequency, and vice versa also true, guys. Continuous frequency, continuous. Correct? And vice versa also true. So in time domain if it is continuous, then the frequency domain it is what? Aperiodic, guys. So this thing you have to remember: periodic, discrete, aperiodic, continuous, or continuous aperiodic. This is very much important. Okay, and from this you can remember the formula also, guys. Okay, from this we can remember the formula also. Fine. Okay, so now next part we will continue in the next class, guys, because it requires more time, continuous time required. So then next we will see what is a Fourier series. So I told you guys what is a Fourier series. It is an approximation process in which non-sinusoidal periodic signal is converted into the harmonically related sinusoids. This process is known as Fourier series. We will convert each and every non-sinusoidal periodic signal into the harmonically related sinusoids. And why we are studying Fourier series? Basically there are three reasons. One reason I told you guys, and two more reasons are present here, but that we will discuss in the next class. But because it requires continuous, like 60 to 90 minutes, that's why. Okay. So all of you, thank you so much watching me live on Wallah English channel, and please watch that video also I told you guys, just search on YouTube Fourier series animated video. Okay, 15 minutes video is there, or watch only for the first and 8 to 9 minutes only. Okay, for Fourier series. So guys, all of you, thank you so much watching me live on Wallah, and please provide your valuable feedback after completion of this session. And next part also very much important. So next part we will continue into the subsequent module. Thank you guys, thank you so much.